I am here today to talk to you about authenticating your users over the web without passwords and the technology that we as developers have built to let us do that. Bit about me. Is that going to work? Come on. Okay. The old ways are the best ways. Clearly my clicker hasn't worked. This is a bit about me. I work at Scaleway. We're a small European cloud provider. If you want somewhere to put your stuff that's not Azure or AWS, come check us out. And you can find me online. This is the most text you'll see on a slide, apart from some code later on, so I promise no more walls of text. So, talk today, 5 sections. We're going to talk about what WebAuthn is and how it fits in within the other specifications that are related to it, something called FIDO2. There's the FIDO Alliance that has set out all of these guidelines. I'm going to talk about code. We're going to go through the code flows, common registration and authentication flows for actually using this technology. I'm going to talk about hardware tokens, a bit more in depth, like some weird facts, how they actually work. I'm going to talk about passkeys, which are the new hotness, and how they relate to hardware tokens and WebAuthn. And finally, going to talk a little bit about what the future might hold, or what I hope the future might hold for WebAuthn and passwordless authentication on the web. Right, so CTAP, which stands for Client to Authenticator Protocol, WebAuthn and FIDO2. What we've got here is we have a problem with user authentication on the web, and the problem is that passwords suck. Who here uses a password manager? That is much, much better than the general populace, which is to be expected. I think it's only about 24% of people use password managers at all, as some statistics collected by LastPass, I believe. And obviously most people do not use password managers, most people reuse passwords. This is insecure, we all know that, I don't have to tell you that. We do have a potential solution though, and that solution is public key cryptography. So public key cryptography, just for anyone who is not aware, you have a private key and you have a public key. You share your public key. Other people can use their knowledge of your public key to verify statements that you have signed with your private key and confirm that you actually have ownership of that private key, which is just a piece of data, it's just a file. So this is a way that you can prove ownership of a secret without having to reveal the secret. And the way that we'd like to use this in user authentication is with hardware tokens. And hardware tokens are a thing created by lots and lots of very clever people, lots of very clever analog and digital circuit engineers. And what they are is a physical object that represents it represents a lot of key pairs. It represents essentially a private key. So you have your private key and public key, and your physical object is what you use to do the cryptography of signing something so that your people with your public key can verify that you actually did that. This does all of your cryptography on an actual physical device, and that's pretty cool for reasons I'll come back to later. And this is something you have. When we talk about user authentication, we sometimes talk about things you know, things you have, and things that you are, like biometrics. Passwords is something you know, and a hardware token is something you have. And it's actually one of the few things we can make that satisfy that requirement. I think that's pretty cool. So when we do authentication with one of these, what does it actually look like? You have WebAuthn, and that dictates how the browser of a web application can make requests of a hardware token that's plugged into a computer. You have CTAP, that's set out by the FIDO Alliance, which determines how the hardware token talks back. And together, these two specifications are called FIDO2. And this is kind of a branding term. So WebAuthn is set out by the World Wide Web Consortium, and CTAP was made by the FIDO Alliance. And if you see something that's saying, oh, this is FIDO2 certified, like a hardware token, that's actually kind of a misnomer. What it actually is a hardware token that conforms to CTAP. But FIDO2 is great branding, and it stands for, I'm trying to remember what it is, fast identity something something. Doesn't really matter is the point. But if you want to use, let's say you have a hardware token, like a YubiKey, and you want to use it, WebAuthn is the interesting bit of this for us as developers because it's the bit that we actually have to implement and know about. You have a server, and then you have a browser running on a computer, and that's where, so the server is serving a web app, the browser running on a computer is accessing the client of that web application, and then you have a hardware token that the user owns. So if a user wants to log in, they go to that web application and they say, hello, I would like to log in. The web application then sends a request to the server saying, hey, somebody would like to authenticate with this hardware token that represents a private key. Do we have a public key on file for them? And if you do, the server can send back a challenge And this is just some data, essentially, including random bits of data that don't mean anything, but the server expects to get back exactly untouched. So the server sends a whole chunk of data over to the client, and then the client forwards that directly onto the hardware token, which the user has plugged into their computer or is using Bluetooth or NFC, some way to connect this device, this hardware device, to the computer that's running the browser. And then the user has to perform some kind of authorization gesture. Maybe it's putting a fingerprint on something, maybe it's just pressing a button on a YubiKey. So the user says, yes, I would like to use my hardware token to do all this cool cryptography. And then the signed response gets sent back to the browser, and then that sends it right back to the server, and the server is able to use its knowledge of the public key corresponding to that private key to verify that it was in fact the user who signed that response, and that the response that it got back matched the one it sent out. That's the purpose of those random bytes. It's something called a nonce, sometimes in cryptography and security. So the server is able to do that, it's able to verify that. Server is happy, and the server goes back to the client, and the client now knows that the user is who they say they are because they've proved it with the ownership of this physical token, and you are now logged in. So WebAuthn and CTAP are the bits that correspond to that side of the diagram. The communication between the client and the server, and what the server actually does in order to verify those responses, is not covered by these specifications, but there are lots of frameworks out there that handle it for you. There's plugins for Spring Boot, for Django. Later on in the talk, I sort of put a screenshot up of some of the libraries that are out there supporting this. So that is the high-level overview of the technology that I'm going to be talking about more today. Does anyone have any questions at this point before we go further? Grand. Either everyone's asleep from the pretzel food coma, or I'm doing all right. So let's look at some code. This is, the first one to look at is registration. So this is when a user wants to create an account or wants to add a new hardware token to an existing account on your generic web app. This is the function that we're going to be looking at. It's not actually that long. I've collapsed some of the code blocks just so you have an overview of what we're looking at. If you want to follow along with it online, you can go and look at the WebAuthn specification, and it's under the typical code, like example code flows sort of section at the beginning. So, first line of this code, check that your browser can even do this kind of thing. Great, grand. If it can't, throw an error, move on. Easiest slide of my life. The next section is where you set up, and this is JavaScript that's running in your browser, right? You are setting up some parameters for a public key that you want your user to create in order for you as the web application to store that as knowledge of who they are. So what you're storing here, what you're doing here is you're setting up lots of different things like the way that the public key, the way that the hardware token will be able to identify itself to you in the future, things like what algorithms you're going to let your public key, your hardware token use, like cryptographic algorithms and so on. And we're going to go through this bit in more detail. So to start with, we have that challenge that I was talking about that includes some random bytes generated by the server. And this is the bit where they're generating random bytes so that when they get the response, the server gets the response back at the end of the flow, it can match those up and go, this wasn't tampered with. So that's actually a pretty load-bearing part of the whole operation, but it's just one line. Next, we have the relying party is the browser, is the web application in this case, because it's relying on the specs and it's relying on the identification of the user by the hardware token. So the relying party is, okay, when my hardware token generates a new public-private key pair for this user to use, I want it to have a name associated with it so that these keys are not used cross-domain. This is one of the features of hardware tokens. They actually generate a new key pair for each account that you use them with, and this means you can't track people across different sites. It provides very strong phishing protection. This private and public key pair that's about to be created is only used on one site, and if the name doesn't match the request when you make a request to that hardware token, it won't do the cryptography. So if you go to misspelled example corporation, like let's say you put 2 X's in there, and you try and somebody's made a phishing website with this fake example.com or whatever, and they try and get you to use your hardware token to authenticate in order to steal your credentials, doesn't work because we've told it exactly which client this hardware, this key pair is supposed to be used with. So that's what the relying party is doing in these parameters. Next, we have a user. We give it an ID, we give the user an ID, and this gets used later to make sure that people don't create multiple key pairs for the same account or the same service on the same hardware token, because that's inefficient, you don't need to do that. So we actually, later on in the flow, you can see where that's actually not allowed, and in order to disallow that, you need to give it an ID. You also have a name of the person that the account is associated with. This is, I think, the only modification that I made to the original code flow, is I changed that name. Cool. Any questions there before I move on? I feel like I'm going quite fast here. We good? We're good. Okay, more parameters for the public-private key pair that's about to be created. The public key credential parameters here, the only type that you're allowed to do is public key, and the algorithm is something you can actually set. Different hardware tokens will have different algorithms that they support. We'll get onto that a little bit later. And you, as the person who is requesting the creation of a new public key, as the relying party, can say, I only accept this, I only accept ES256 ones. Or you can say, actually, I'm all right with various ones. For certain security reasons, maybe you might want to only allow specific algorithms to be used in the cryptography that's involved here. So authenticator selection is interesting. So this is a parameter that determines whether or not the user has to do a specific action to the hardware token when they authenticate themselves. So a YubiKey where you just press a button, that verifies that somebody is present. That's user presence. But one where you have your thumbprint on, that verifies that it's actually you. So that's user verification, and that is a stronger condition. Because somebody can just take my YubiKey and it won't be me that presses the button, but they can't press it with my fingerprint. So there's different levels of how strong security you are requiring here in the use of these hardware tokens. Not all YubiKeys have, or not all hardware tokens have biometrics on them, but some do. But there must be some user gesture that is performed by the user in order to make the hardware token do its thing. And this is so that if you have a hardware token that's left plugged into a computer, if your computer's then riddled with viruses, it can't just like spam the hardware token with loads of requests to try and reverse engineer the private key. I mean, that would be very, very difficult anyway, but requiring a gesture from the user every time it performs that cryptography guards against that completely, essentially. So that's what that parameter is doing. And then you have a timeout. Once you've made this request to the hardware token, if you wait for 5 minutes, this request will expire. Just kind of standard, you don't want things to hang for ages. These requests are processed synchronously. So that's also a reason to have a timeout on here and consider that as part of like your user experience. Depending on whether or not you are requiring user verification or user presence, so just pressing a button versus a specific fingerprint, for example, the WebAuthn spec actually recommends different timeouts, which I think is pretty cool. It's like, oh, for user experience, you know, maybe it takes a while to get the thumbprint right. Like, don't give them only 30 seconds to do that. Maybe they're wearing gloves or something, I don't know. So that's what that parameter is doing. And now we have got to the end of our, oh no, we haven't. This is the excluding the credentials that I talked about earlier. So let's say I have a hardware token and I'm going to my favorite yarn store, right? And I spend a lot of money here, so I want to secure my account. I don't want anybody to know the exclusive hand-dyed yarns that I've been buying, whatever. I've got a hardware token that I've secured this account with. But then I sort of go, I forget that I've done that, and I go, oh, I've got a hardware token, I should use that to secure my account. And I try and create a second key pair for the same account with the same user on the same client, the same web application. This is a mechanism to stop that from happening, because it's just a waste of space on your hardware token to store that extra key pair. It's not doing anything for you. I don't know why there are two here. There are, it's the example flow, whatever. But that's what that's doing, essentially. You can also exclude credentials that were created with an earlier version of these protocols called U2F. So this is included in the example flow just for sort of backwards compatibility, essentially. Yeah, and you can see we've got the closing brackets there. We are now at the end of all the parameters that the browser is specifying for the new public-private key pair that we want to create on the hardware token. Everyone with me still? Good. Right, so popping back up to the top, sorry, was that a question? No, never mind. Popping back up to the top level, you can now see that we've done the first 4/5 of this function. And we're now in the last little code bit, and that is where we've set up all of our parameters, and we're now actually going to make the call to the hardware token. And that looks like this. You go navigator, credentials, create, and you pass in all those parameters. And if you get something back from the hardware token, it means that the user said, yes, please create me a new private public key pair. They've done the authorization gesture, and you have all of this information from the hardware token. You've got a new public key back. So the CTAP is what defines the data structure and the API of that new credential info object. And you basically just send that off to the server to be parsed and stored and handled there. If you didn't get that back, you got an error instead. It means that the user didn't present a hardware token, or they didn't do the authorization gesture, they refused consent, and it's up to you what you do there. Do you retry? Do you say, whoopsie, like Tumblr does with its little cutesy little error messages that send my blood pressure up the skyrocketing? That's up to you as the developer to decide how to handle it. But this is what the actual call to the hardware token looks like, and it's actually really simple once you've set up the parameters. So that is registering a new hardware token to an account in code. The authentication code flow is much, much simpler, in fact, because you're looking for a credential that already exists. You don't have to set up all those parameters. And it looks like this. This is the whole function in the code, in the specification example. So again, you have that first line going, if you can't handle these kind of credentials, don't even try. Great, fine. And in this case, what you're doing is you're going, I know what the ID of this credential is because I have it stored on the server. I know which user it is that's trying to log in. I know that they have a public key stored with me. I know what its ID is because that's one of the values that gets created by the hardware token when the credential is created. So I have that. So you can see it says random bytes previously generated by the authenticator. Not always random, in fact, but I'll come back to that. So this is just a long string that identifies the specific key pair or the specific public key that the server knows about. Then you have some options, and here is where you have the challenge generated by the server, those random string of bytes, again, that it wants to get back exactly untouched and signed by the cryptographic processes in the hardware token. Again, you have a timeout, and you say, I'm only allowing credentials. That allow credentials line is, I'm only allowing the public key with the credential ID that I already know about. I'm looking for this specific key pair. So there you've said, I'm looking for this, and here are the user experience thing of it, of what the timeout's going to be. I'm sending a specific challenge to it that I expect to get signed back, untouched, and a valid signature over that. And then you just do the same call, but it's instead of create, it's get. Navigator credentials, get. Give me the public key, do the thing with this public key. And if you get back what's called an assertion, which is when the hardware token signs that challenge, sends back that challenge and the signature over that challenge, the server uses the public key, its knowledge of the public key to decrypt that or to verify that, and knows that the challenge it got back is the same one that it sent out. All is well in the world and you are authenticated. If not, again, the user didn't have their hardware token or they refused consent. So that's actually the entire flow of using a hardware token to authenticate with an existing key pair that you already have stored on the thing. It's actually really, really simple. And this is partly because the WebAuthn spec is actually really well made. So that is code. Next up, hardware tokens and usability. So this is where I get into my opinions about these things. They do have some usability concerns, which I'm going to talk about, that you can lose them, they're expensive, things of this nature. But what a hardware token actually is some flash memory and some secure crypto processors, which are very complicated circuit boards made by some extremely clever people who I hope are far more highly paid than I am. And that's a photo of one of them. And you can see where it's from. It's from a specific, I think a TPM actually in a laptop this one is from. And these crypto processors are what allows the cryptography to happen on the device without the private key ever being at risk of leaking out into whatever device it's plugged into or embedded within. So you get hardware tokens that are actually embedded within laptops and within phones. If you've got a fingerprint scanner on your phone, what that's actually doing is hooking into a hardware token. But these crypto processes are within a hardware and software boundary that does essentially the same thing as enforcing CTAP on roaming authenticators or USB keys. So that's what the hardware tokens are physically made up of. They've got flash memory to store the public-private key pairs that are generated and things like addressing the memory and all of that. And these crypto processes that are actually where the magic happens. So yeah, unencrypted private keys never leave the device by design. There have been attempts by various I forget which way around it is, like blue team attackers or something. Anyway, people who've gone, I wonder if I can break this, and they've gone and taken apart the keys physically and tried to extract private keys out of them. And they were able to, but they so destroyed the device in the process that they would no longer be able to use that knowledge in order to do any kind of actual attacks. So that's very cool. That's actually, I think that's extremely cool. So you have a dedicated key pair for each identity. So there is a master private key that lives within this thing, but for each new account that you want to use it to register with or authenticate with, it'll generate a completely new key pair. And one of the things I mentioned this earlier is that gives you is you can't reuse the same private public key pair with different identities. That's essentially the same as you can't reuse passwords. If somebody did somehow manage to get hold of one of these private keys, they wouldn't be able to reuse it in any of the other places to use the hardware token to authenticate, unlike somebody busts your password, you're on Have I Been Pwned, and then they go and stuff that password into every other account they think you might have. So there's very strong protection against credential stuffing. It also means that if you are somebody who worries about having your identity tracked across the internet, somebody going, oh, I see you've made purchases here, and you have an account there, those are all different public keys. They can't be linked to each other. Obviously, I sign into everything with Google, so I lost that privacy battle a long time ago, but if you are someone who cares about that, these give you that as well. Something that is not usually a concern these days because flash memory has been getting much better and we've been getting you can store loads of memory on like tiny, tiny things. But the number of possible key pairs, you can store arbitrary numbers of these. Technically you could store infinite. You could max out the memory of the flash drive that forms part of your hardware token. This doesn't really happen in practice, but there are a couple of keys that do clever things in order to get around this. So some hardware tokens do a thing called key wrapping. This bit that I mentioned earlier, I said, okay, these are the random bytes generated by the hardware token when it creates new key pair. And this is like an identifier for the public key. They're not always random. Sometimes what the hardware token does, and I forget, I could not Google it for the life of me, but there is a brand of hardware token where what they do is it generates the new key pair, and it uses its master private key to encrypt the new private key and sends that as the identifier. So the server that's storing the public key and all the metadata around it is also storing the private key without knowing it, but that private key is encrypted by the master private key of the hardware token. So when the request comes into the hardware token and it goes, okay, sign me something with the private key that corresponds to this public key, and this public key has an identifier. The hardware token takes that identifier, decrypts it with the private key, uses that result to sign the challenge and send it back. So it never has to store the private keys on its device. And I think that's just really cool, like daisy chaining cryptography. And it blows my mind that that is secure, but it is, and I think that's really neat. So that's called key wrapping, and some keys do that. Right, as I mentioned, hardware tokens, they can be physically lost. I have mad ADHD. I am constantly putting things down and just losing them instantly. It's a miracle I've managed to keep hold of my YubiKey as long as I have. It's mostly because it's on the same keychain as my house keys. But you can physically lose them, and if you do, you lose all the key pairs that you've been using to authenticate with your accounts across the internet. This is bad. They are expensive. So one of the mitigating factors, I did an episode of .NET Rocks a year and a half ago with Rich Campbell and Carl Franklin where we talked about this stuff, and Rich told me that one of the things that he does is he has like 5 YubiKeys, and they're all like labeled with hashes or something. They've got identifiers on them. So if he loses one, he always registers more than one to one account. So if he loses one, he has a backup so he can still get into that account, register another. I'm like, like, I could afford to buy 5 YubiKeys. I really don't want to, and it kind of just exacerbates the problem of losing them, because I'm like, not only where is my YubiKey, but where is that specific one, right? So for some people, maybe that's the solution, but certainly not for everyone. They also add friction to the user experience. If I really, I've just had a bad day and I want to go and buy some expensive hand-dyed indie yarns from my favorite yarn store, and I have to go upstairs and get my YubiKey and hunt through my drawers and find the YubiKey and make sure I do that within 5 minutes because there's a timeout on the WebAuthn side. That's really annoying. That's a bad user experience. We as developers generally like to try and avoid this, because if people have bad times using our apps, they use them less, and then our shareholders make less money and we get laid off, and it's bad. So user experience does matter here, and while these are incredibly secure, they are also not appealing to people, and people will not use them because of this friction, and then they're not adding any security at all. So, any questions now? I keep pausing just because I feel like I'm going very, very fast. But question, yes?
Perhaps a quick question, the answer may be complicated.
Yep, go for it.
U2F, so the old 501, didn't need flash memory because it could derive the private key from the server name.
Oh, so U2F, the previous version, didn't need flash memory because it could derive the private key from the server name. Is that what you said? Why wasn't that enough? Good question. I don't actually know the answer. It might be because there were advances in hardware token manufacture. Does anyone know the answer here before I go and speculate? Cool. It may be that because there were advances in hardware token manufacture that they gained new capabilities and we needed new specifications to handle that. I know that there is some interoperability between U2F and FIDO2. I don't know is the short answer, but that's a great question. I will go look it up and tweet about it. But thank you very much. Any other questions? Cool. So now we get to one of my favorite bits of this talk. Passkeys. Who's heard of these? Okay, not everyone. Interesting. So passkeys this is the official logo for Passkeys. If you're talking about Passkeys, you need to be using this logo, otherwise someone from Google, Microsoft, or Apple are going to come and hunt you down and make you put it on your slides. So this is a joint venture between Google, Microsoft, and Apple. They're the current people who are driving this, or current corporations who are driving this. And what this is an idea of storing a cache of encrypted key pairs in the cloud. So if you have a Google account, a Microsoft account, an Apple account, somewhere, on one of their servers, somewhere, there is a hard drive that's got all your cloud data on it, or it's probably distributed across many. But somewhere, there is a bit of the cloud that hosts all of your data, and in that bit of the cloud, they will put a bunch of key pairs. They won't just put them in there raw, they are encrypted with the password to your Google or Microsoft or Apple account. They're not encrypted with a public-private key pair. They're encrypted with the password to your account. And what happens when you want to use these key pairs to authenticate is that you can decrypt and use them as needed. And the way that you say, as a user, I would like you to decrypt these key pairs and use one of them for this WebAuthn process, is that you have your phone, or a laptop that is registered to that account, Google, Apple, Microsoft, and that also has a hardware token in it. It's got biometrics, it's got Face ID if you've got your fingerprints. And so the flow of unlocking stuff, the flow of authenticating with this way works like this. So for these diagrams, I've put the server and the client together essentially because they act as one entity. The bits in between don't really matter here. So what happens if I'm using Passkeys and I want to log into my yarn store? I go to my yarn store and I say, I'd like to log in. And the yarn store goes, cool, I noticed that you have a public key registered with us. Would you like to use the private key to log in? And that request goes to the Passkeys store for my account. And the Passkeys then forwards that to me and says, hey, on your device, would you like to log into this using one of the Passkeys I have registered for you? If you would like to, you must use your registered hardware token that's part of this device that's registered to your account to unlock them. And you do your fingerprint, you do your authorization gesture, which ideally is a biometric. I know some have pins, but ideally it's a biometric. And you say, yes, please unlock the key pair you have stored for me in the cloud, please decrypt that and use that to do the WebAuthn process. So that consent gets sent back to the Google Cloud or whoever, and then the WebAuthn process happens between these two parties. So that's what passkeys are. They are store these key pairs in the cloud, not on a device. And there is a weakening of security here because the Google Cloud security is less secure than the secure crypto processors, just kind of by dint of the secure crypto processors being like as impossible to crack as anything we've ever built. However, I do trust Google Cloud's security or Apple or Microsoft pretty well. So that's the kind of security posture of these things. But what they get you for that sort of slight weakening of security, oh yeah, and once that happens, then you're logged into your account, yeah. This protects against device loss. Because all those key pairs that you're using to authenticate across different places, across the internet, are actually also stored in the cloud. If I lose my phone, I haven't lost all those key pairs. As long as I can get into my Google account without loss of generality, let's just say Google, as long as I can get into my Google account and register a new phone or a new hardware token, like, I actually think my MacBook probably has one when I log in with a fingerprint, right? As long as I can get into my account, register a new platform hardware token, a hardware token that's embedded in a device, registered my device to that account, I can get back into my key pairs. So if I lose, it's not the same risk as losing my YubiKey, because those key pairs are actually synced across all of anywhere that I can get into my Google account. This also has the added bonus of most hardware tokens, I think all hardware tokens that are built into devices, platform authenticators they're called, require biometrics. And biometrics inherently require user verification, so you are who you say you are, not just you are a person pressing a button. They're doing user verification, not just user presence, and that is a stronger security consideration, that is a stronger requirement. Only I can use my phone to unlock my passkeys, or I don't know. Do identical twins have the same fingerprints? I actually don't know that. Anyway, only I can use my fingerprint scanner to unlock my passkeys, unlike somebody can nick my YubiKey and use it to log in as me. Currently, however, the state of passkeys is such that we are dependent on corporate cloud vendors. So if you are somebody who is worried about being tracked across the web, and that's why you have a hardware token, is because you want to have different public keys for every account that you use, and you don't want to be tracked across all of these different services. This isn't going to work for you, right? You are, again, I lost the privacy battle against Google many, many years ago. So, that's not a concern for me, but it is a concern that we should have, and it's a concern that is reasonable to have, and one that we as developers would do well to take into account. Yeah, if you are already fully bought in to Apple, for example, Mark, who's doing the closing keynote today, was telling me today that his whole family is on Apple. He's just given in and gone and got an iPhone and a Mac and everything. He'll probably be absolutely fine using passkeys stored in the Apple cloud. But it is a concern. So the user experience of passkeys is much, much nicer than roaming hardware tokens like YubiKey. Because if I'm going to log into an account on my phone, all I have to do is use the fingerprint scanner that I've got right in front of me. If I want to log into a computer that doesn't have a hardware token registered to it, I've actually got a couple of options that passkeys that, none of this is yet standardized, but it's all stuff that, like, I think Google in particular is kind of leading the charge on this. Let's say I've gone to my local library and they've got some decrepit old, some old monitor, it doesn't have Bluetooth, it doesn't have NFC, it doesn't have anything. And I want to log into my yarn store and buy myself loads of yarn. And I'm using passkeys to do that. What I can do is I go to that website and it says, would you like to use a passkey to log in? What it can actually ask me to do is to scan a QR code on my phone and then do the verification on my phone, which has the hardware token. That gets sent back up to the server and it knows that I have done that gesture of consent, that authorization gesture. So even if you cannot like connect your phone through NFC or Bluetooth, because those are also options for using your hardware token on your phone to verify with other devices using this method. Even if you don't have those, you always have QR codes, because your computer will always have a display in your phones. If your phone's camera works, you can do that. So these are also cross-device authentication mechanisms, and without you having to buy hardware you don't already own in order to do this. So you get all the benefits of a hardware token with user verification, biometrics, something you have and something you are, without having to buy new stuff, without having to go hunt down a YubiKey, plug it in every single time. Maybe you have to unplug something because God knows my cable management is an absolute disaster. You know, none of that, it's just your phone. And this unlocks hardware token authentication for a lot more people. This is suddenly going to become a much more palatable option to people who are not here in this room, techies, already bought into the idea of maybe even cryptography at all, right? And this is a good thing. More people having access to strong authentication that is not going to be threatened by them losing their phone. This is good, just in general. This is a really good thing. User experience does really matter for adoption, and when we build things, we want people to use them, because otherwise we get laid off. If something is hard to use securely, it doesn't actually increase security. I touched on this earlier. If I don't bother using my YubiKey because it's a pain in the ass, I might as well not have one. So this is a way to, although, as I mentioned earlier, there are some security weakenings with using passkeys versus just using a YubiKey every time, that doesn't matter if the person was never going to use a YubiKey in the first place. So making strong authentication by hardware tokens more available to more people is going to make it happen for more people, like, period. So, where next for passwordless authentication? Currently, passkeys are not widely used. I would hope for wider adoption. There you can go to, I think it's passkeys.io, and they have a list of like who's actually using these, and it's not a massive list. It's like 20 or 30 places. What we'll need for this to happen is more developer education. Those of us who are building these kind of websites need access to libraries that are going to handle them on the server side, because there is a slight difference in how you want to handle them and store them. You want to know what libraries there are for your favorite backend, for your favorite server framework. You're going to want to see lots of examples, lots of different flows, how to handle failure cases, all the developer content that I, as a developer advocate, know and love and sometimes create. So we need more of that. There's a list of contributors on passkeys.dev. So lots of people you can go and like look at on Mastodon and Twitter and who blog about this stuff if you want to know more. More of this kind of content is coming out, and we need it if this is going to get adopted. We also need more people actually building libraries to handle this stuff. So on the front end, the code that we looked at for handling hardware token authentication pretty much like translates one-to-one. It's the same mechanisms like WebAuthn. But there are certain nuances, and on the back end there are definitely nuances. So we need more libraries to handle this different workflow if we want more passkeys to get used. And we need development time to make it happen. As developers, we can't go and say, I want to make passkeys work in my web application if your skip level is not buying in and giving you the development time that you need and the points in your sprint to make it happen. So these are the barriers I currently see to wider adoption of passkeys, which I think would be pretty much unmitigatedly a good thing as long as we have cloud infrastructure. Another thing I would like to see is open passkey stores. So what I mentioned about being beholden to Google or Apple or Microsoft for your passkeys, they will own even more of your life than they currently do if you use them. One way around this is to use things like Bitwarden or NPass or LastPass or whoever. So I had a quick look at to see what the current sort of state is of open password management and where they're going with passkeys. NPass and Bitwarden both have released blog posts saying this is very nearby on their roadmap. So I've got this screenshot here from the Bitwarden website saying, yep, it's right around the corner, yeah. So we'll see if that bears out, but they have made commitments to doing this, which is really encouraging because it means that people who do really care about not being even more in the pocket of big Google, the one I keep going back to because I am in the pocket of big Google, people who care about that are going to be more able to adopt these and have control over their own data. It will ease enterprise adoption as well. I don't know if you guys have your IT departments just, data sovereignty is good. The IT departments believe this wholeheartedly, I'm pretty sure. I know that my own IT department, if you want to give away company data or store company data anywhere else, they get very itchy about that. So being able to stand up your own Bitwarden server or Vault Warden server, or whatever it is, and manage passkeys for your work accounts, that's going to ease enterprise adoption, and that's also good because it means that fewer companies' data will get stolen, which is also nice. And yeah, data sovereignty is good. One of the nice things about hardware tokens is that you hold all that data in the palm of your hand. One of the bad things about it is you hold all that data in the palm of your hand and you can lose it. So being able to have the benefits of both worlds, the resilience of a cloud-managed set of passkeys without ceding control over that data, that would be really nice. So I'm excited to see more open user authentication management companies and tooling adopt passkeys as well. So, wrapping up, bit ahead of time, but hey-ho, more time for questions or to go and grab coffee before the keynote. We have learned about what WebAuthn is, how it fits into the security landscape, and how it works. We even looked at some code. We looked at current options for key pair storage. You've got your hardware tokens and you've got passkeys. And we've talked a little bit about where we might go next, what I hope to see, why I hope to see that, and things to look out for if you are interested in this stuff. You can go and find really interesting people on this topic to go and follow and see what they're saying about the future state of passwordless authentication. Thank you very much.